I want to go ahead and introduce Denny Quist and Lorie Liebrock, and we're going to talk about reverse engineering by Crayon.
All right, hello everybody. This is reverse engineering by Crayon. I'm going to talk to you about some of the hypervisor-based malware analysis and visualization. My name is Danny Quist. I'm the founder of Offensive Computing, also a PhD candidate at New Mexico Tech, and my day job is reverse engineering and also teaching reverse engineering.
And I'm Lorie Liebrock. I'm the chair of the computer science department at New Mexico Tech and associate professor. I also run the Scholarship for Service program there. So if you heard the keynote speaker talk about New Mexico Tech's SFS program, you can see me later.
It's basically free money if you indenture yourself to the government. Okay, so let's talk about this talk here. We're going to start by talking about the reverse engineering process. Then I'm going to explain a little bit about hypervisors, and then talk a bit about Zen and Ether, and then how those tools help modify the process. Then I'll get into my visualization tool, Vera, and then we'll look at some real reversing that I did with this, and then talk about some of the results from it. Okay. So let's start with the reverse engineering process. This isn't a standard method, and I don't think there is such a thing as a standard method. This is just a method that I use that works well for me. I also, when I'm teaching reverse engineering courses, this has been something that's been good for my students. So the general process starts out by setting up an isolated environment. This is using something like VMware or Zen or Virtual PC or dedicated hardware. The next portion is the initial execution and analysis. I run the malware, see what it does using tools like sysinternals or CW Sandbox, looking for any sort of operating system state change like files, registry, that sort of stuff. The next thing is deobfuscation or software de-armoring. This is taking any sort of packer and removing it so that you can actually run it in tools like IDA Pro. And then next is the disassembly portion. This is IDA Pro and Ollie debug. And then the last one, which is identifying relevant and interesting features. This is just experience-based, something that you build after having a little bit of time in front of a doing reversing. So this talk is going to address two main points. The first one is going to be this deobfuscation and software de-armoring. We'll talk a little bit about what Zen or how specifically Zen and Ether are used here. And then the second one is the identification of relevant and interesting features. Okay, so the isolated analyst environment, I won't spend too much time on this, but generally you need to have some sort of way to protect yourself from this code that's running on the system. So things like VMware, Zen, KVM, that sort of thing, just some way where you can roll back there. And also it helps to create an own good baseline so you know what you're doing. And if something bad happens, which it does a lot, you want to have some way to have at least some idea about how to backtrack when that happens. Okay, execution and initial analysis. The goal of this is to quickly figure out what's going on in the program without looking at assembly. A lot of the techniques out there are the low-skill reverse engineering rely on this, and generally it's a good idea to keep from staring at code whenever possible. So just looking for changes to the file system. Written files, change to the behavior like network traffic, whether the performance of the system's on there, whether there are ads or other change browser settings, and also looking for porn that you didn't put on the system yourself. That's a good sign. Okay, so the next one is removing software armoring. So these are just protections to either make the program smaller or more likely prevent reverse engineering. These are done via packers, typically, which are just small self-modifying programs that encode or decode information. There's been a lot of research on this. Some big ones, Ollibone by Joe Stewart, Saffron, which I talked about in 2007, PolyOnPack, Renovo, Ether, and Azure. This research here is going to be using Ether. Okay, so all a packer is it's a small self-modifying bit of code. It's got a small decoder stub, which is going to decompress the main executable. And once it's done doing that, then it's going to either restore the imports or It's either going to restore the imports or dynamically load them. But one of the other things that they do is they play tricks with the executable, and they play tricks just to munge up or confuse any sort of disassembler. So, I mean, there's been a couple talks here at the con that have shown how to play tricks with IDA, and so that's what's going on here. Okay, so you start out with a normal PE file that has some normal code. In this case, the entry point is going to point to actual valid compiler-generated code here. A packed file is just going to look slightly different. It's going to take that code as it exists, modify it and change it, and then insert a small decoder loop at the very beginning. There's a couple of other protections out here that are worth mentioning. So virtual machine detection, this has been talked about a lot. Red Pill and OCVM Detect are two of them. There's a very good paper that I wanted to point out. If you guys haven't read this yet, Attacks on Virtual Machine Emulators by Peter Ferry. What Peter did is he went through every single virtualization product and figured out how to detect it with usually no more than 10 instructions of assembly. So this is a very good paper, and if you're going to write anything that's going to subvert this, this is a good way to start. See, then we have the debugger detection. This is things like looking at the process execution block to see if the isDebugger present flag is set, and also looking for the trap flags inside of the E flags. Timing attacks, by looking at the time step counter inside of your code, you can measure the time between when you take that initial view of the time step counter, execute a couple of instructions, and then look afterwards. And if it's something like a couple seconds, which is usually me pushing the F7 or the advancing to debugger, that's a good indication that it stopped. Or any sort of automatic analysis system that's taking a lot of time and not preventing that. The goal here is it tends to be very effective at finding anybody and analyzing it. So to get around these, we basically have two different methods. The first one is that we can play the fun game of finding out all the protections that are inside of a system and disable them by hot patching code or that sort of stuff, which sucks. Or we can make ourselves invisible, which is pretty much the goal of any of these systems that we're using. So I, of course, am going to take number 2. And so to do that, there's a couple of virtual machine monitoring systems. Some of them are software-based, so Renovo and PolyUnpack, and I believe that the Zynamics box unpacker, and if I have our arrow here, they can throw something at me if I get this wrong. These are all the software-based systems. But there's a couple of problems with this. You know, looking at Peter Ferry's paper that he published out there, detecting these sort of things is almost trivially easily. So you either have to modify the virtualization system to allow or prevent that sort of thing from being detected, or find some other way to get around that. The base problem is that the Intel CPU was never traditionally designed for virtualization, and so they don't emulate the x86 bug for bug. The hardware virtualization, which I am going to be using later in this, does take some steps to prevent that, but you know, that was added on as an afterthought. Okay. Operating system-based monitoring, so these are things like Saffron or Olibone. What these do is they abuse the page fault handler in a running system to achieve some sort of single stepping or control over the running process. So typically what happens is that they abuse the supervisor bit to generate page faults on every single execution, intercept those, and then get that. The problem with this is that the only area that you actually get these executions on is based on the page boundary. So as long as you're happy with the 4K page boundary, that's okay. The problem was, which I ran into with Saffron, is that it destabilizes the system. So once you put Saffron on, you set these page mappings and run it, you can basically run the program exactly once, and that causes some problem. So you need dedicated hardware for this, and without the fine-grained monitoring, it really prevents some of the more interesting things that we can do. Okay, a fully hardware-based virtualization is Ether. This was written by Artem Dynaberg and Paul Royal. This is a Zen-based hypervisor system, and it monitors system calls, instruction traces, memory writes, and all that sort of good stuff. And it deals with the program by looking at the memory page mappings. This too requires dedicated hardware, but the dedicated hardware that it requires, you can actually like start and stop VMs, and you don't have to reboot every time you want to analyze this. So it's much more conducive to an automated analysis environment. Okay, so back to the reverse engineering process. When we get to things like disassembly and code analysis, this is the part where it's very nebulous. And I noticed something teaching to a whole bunch of students. This is something that was really hard to convey to them, like what they're looking for. So if you reverse F for a while, you get a sense of intuition about what you're doing, but until that, it can be quite tedious, especially if you don't know the instruction sets or that sort of thing. And one thing I noticed is a lot of people in my classes tend to focus on the instruction level view rather than taking a big look and seeing that. So you kind of miss the forest from the trees. And analyst fatigue, the level of attention required yields fewer results and makes things a little bit more difficult. Then the next portion, which is finding interesting and relevant portions of the executable. This is another intuition and experience-based process, which we're trying to avoid. Some typical starting points that are used are look for interesting strings, look for any sort of API calls that are interesting, or look at any interaction with the operating system. But again, this is fundamentally precise, and it's tedious, and it's frustrating for beginners. So we'd be looking at a sample, and I would say, okay, well, what's this thing doing? And they'd say, oh, that's the exact portion that I'm interested in. But how do you develop that sense of understanding? Okay, so let's talk a bit about hypervisors. So there's been a lot of hype about this over the past few years, and it's definitely a buzzword I think is overabused, including in my talk. So the big thing is that hypervisor rootkits are leading to defensive tools. We've seen this in a lot of examples when we've looked at other technologies that have come around. This sort of thing has really been leading the defensive side. So we're going to take something that's being used for offense and take it over to the defense side. But what's nice about this is that all the methods that are used for hiding yourself from a running process to prevent detection of the hypervisor-based rootkits can be used to actually prevent a piece of malware from detecting that we're there. So also detection of hardware virtualization is out there. It can be done. I just haven't seen it implemented very much. Okay. A couple hypervisor-based implementations I played with going along with this is VMware's ESX server. It's a commercial-grade solution for VMs, and I think it's powering most of the cloud infrastructure that's out there. And this avoids a lot of the VM detection tools. The next one is the Linux kernel virtual machines. This is a separate analysis operating system from the target OS. This is, when I'm doing my reversing, this is typically how I like to sit in there, and that's just to prevent me from accidentally executing malware on my home box, which doesn't happen often, but when it does, it's hilarious. But one thing I like about KVM from an academic point of view is that instead of re-implementing a lot of the base operating system algorithms for managing resources, it uses the stuff that's built into Linux already. So it uses the Linux memory manager, the Linux scheduler, and that sort of thing. And I think it's the exact right way to do it. And there's not too much in the way of recompiling a base hypervisor all over again. It's just a module that's loaded into the kernel. Zen, I believe this is one of the first hypervisor-based systems. This has some excellent tools for introspection. It uses a standard QEMU image format, so you can manipulate that after it's run. But the nice thing is that it's got an API that's fairly well integrated with Python. So a lot of the reverse engineering tools are written in that, and it makes it a little bit easier to interact with it, and it's very good. Okay, so let's talk a little bit about Zen and Ether. Okay, so what is Ether? Ether is a set of patches to the Zen hypervisor that are built to instrument a Windows system. So the modules that are available are instruction tracing, API tracing, and unpacking. And there's a very, very good paper that was written about this at an ACM CCS conference, which was malware analysis via hardware virtualization extensions. So, a lot of times the academic, the content that comes out of those is not very good, but this paper is excellent. If you haven't read it, you should already. Quick show of hands, have anybody read this? Okay, good. 4 people, awesome. So that's your homework for tonight, is to go look at that. Okay, And you can do it with a beer too. So Ether's event tracing system, this is just trying to detect any sort of events. The big first one was system call execution to look for reads and writes on a file system and that sort of thing. Instruction execution, so as a system's running, it'd be really nice if we could watch that. Memory writes, and also context switches between processes. So it's actually fairly covert. So there's no modifications to the base system, which reduces the detection landscape for the entire program here. So that makes it a much more, it makes it a much better system for looking for any of these changes. Okay. Instruction tracing is implemented by manipulating the E-flags register. It sets the trap flag on a running system, and basically every time there's a trap, it's going to intercept that, log it to its local system, and then allow it to continue executing. So the way it prevents programs from looking at that, or looking to see that it's actually been executed, or that this trap flag is set, it hooks the push F and pop F instructions on the running system. So this is the ways for looking at the trap flag. So this effectively hides the single step process. And the time step counter implementations are also watched by the TSC portion by hooking the RDTSC instruction and modifying the values so that the time is dilated correctly. Okay. Memory writes, these are tracked by manipulating the shadow page table that Zen uses for its for managing its memory. So this gives access to any of the written and read memory addresses as it's going, and uses a very similar process as Saffron and Olibone used. System calls. The system call process on Windows uses the sysenter instruction, and this instruction, or the sysenter EIP, is going to be pointed over to the to a bogus page address or a non-page address, which will generate a page fault. And then once that page fault's generated, it's going to log that and return it to Ether. The other thing that they did is looked at the int2e interrupt to catch some of the older system calls. Okay, so the Ether architecture starts out with a Linux DOM 0, and if you're not familiar with Zen, DOM 0 is just the management or base running system inside of Ether. And inside of there, you get access to the VM disk images, which are running on the system, and then the Ether management tool. So this is how you watch a process that's running. The Zen hypervisor then sits below that, and that's where the Ether patching system's at. And then we have the instrumented Windows XP SP2 system. So this red block right here is the actual place where the malware is going to be run and analyzed. Okay. So when Ether came out, it was in a form that was actually very useful and provided good data dumps. But there were a couple of issues that I had when I was trying to use it for my actual reverse engineering. So to fix, and mostly the issues were that I couldn't actually load it into IDA, which made things difficult. So what I did is I moved the unpacking code from the hypervisor into the user space. The hypervisor-based unpacking system was pretty good, but hypervisor's code is scary. So I wanted to move this to user space so I could use things like libraries and hash tables without my computer rebooting. Also added a little bit more user mode analysis. You could look at this. And then the PE repair system. This allows for disassembly of the executables inside of IDA, and then enhanced a little bit of the monitoring system. Okay, so the user mode unpacking system that I put in here, all it's doing is it's watching for memory writes and logging that into a hash table. And then you allow the program to execute as normal. And then once it's executing, you look for any sort of executions into that written memory and then dump that memory. The problem, and this works fairly well, and it'll actually get you lots of what I call candidate original entry points. But the problem is that, and it's not perfect, but it's pretty decent. So you can go through and track all of these and just find one that you can use for doing this. There's a lot of scaffolding in here for future modification for some other stuff I'm doing. PE repair, basically the files that were dumped by Ether had a couple of problems. The sections weren't necessarily file aligned, so when IDA tried to load it up, it had issues reading it. The address of entry point was invalid, so I didn't really know where to begin. And this generally created a harsh problem. But the nice thing is that there's a lot of code out there that's available to start looking at this. So Ollie Dump is the first example. They had some good code, which I ported to Saffron initially, and then I took that code and put it into the user mode component of Ether. So try to fix the section offsets to match what's on disk, repair the resources as much as possible, and then set the address of the entry point to the candidate OEP. And that actually made things a lot better. So the results from this are we get as close as we can to a truly covert analysis system. I will call it nearly invisible, but I know that there's some ways that it can be detected. And I know Alexander's probably thinking of them right now. The blue pill type detections, those are issues. But what's nice is that you get fine grain execution of programs. You can monitor memory and with this, and the dumps can now be loaded inside of IDA. So I mentioned that it's nearly invisible. I haven't actually found a sample that Ether had trouble unpacking. So a lot of the hardcore stuff like the Meta, this gets around that too. Okay, so let me show you Ether here. Okay, so we're going to start by loading up this malware sample inside of IDA. This is just a sample of the Mu worm from a NetBull, or Mu-Pack NetBull virus. And so what that message is it's IDA saying that looks like the imports are destroyed and it's not visible. So we look at the strings inside of here. There's nothing useful. The function calls or the function tables, it basically just has one address right here. The imports are severely lacking, so there's basically get proc address and load library, which are the two basic staples of any good packed sample. And the visualization bar up at the top is missing a lot of data, so there's no blue inside of here, which is a good example of code that's inside of here. And looking at the log inside of IDA, there's no messages that it's found any sort of flirt database matches, so it's going. Okay, so I'm going to go ahead and close this down and then bring up Ether. Okay, so Ether just runs on a Linux system by default. The first thing that I'm going to do is I'm going to copy the file over to the disk image on the desktop. And since Zen uses these QEMU images, you can find copies or you can mount it via the loopback and be able to manipulate the file system fairly easily. Okay, so we've got the testing here. We're going to mount this up, have it run. Copy that over to the desktop so we can find it easily. And then once we've done that, the next thing to do is actually to start up the Ether system running. So in this case, we'll use the XM command. So we just create a new virtual machine image. And the configuration of this is pretty straightforward. Okay. So once it's started up, you get a VNC connection to actually interact with this. So we can see that Windows is starting and running, so we just give that a little bit of time to boot up there. And when everything's set up, we should get a running system. So now we're in blissful paradise and we can actually start some of our analysis. So one of the things that I do is that I start up the task manager so that I can run monitor the execution of the process inside of this here. Okay. Now the next step is to start the Ether interface or get the actual ID. So in this case, Ether uses the ID of the running system. In this case, it's going to be 9. And we're just going to use that to port over to Ether. And so you just say Ether, the ID that you want, the unpack user space module. Then you give it the file name that you want it to watch for, and then a local copy of the file on the system so that you can actually do the unpacking. Okay, so once that's done, the system's up and running. The filter name's been set to mu_netbull.exe. And then at this point, we can go over to our our virtual machine and start the program running. So what I'm going to do is just double click this, start it up, and you're going to see that it's going to take a lot of CPU time. So usually it wouldn't take that much. Whenever Ether identifies that it's matched a candidate original entry point, you'll get a message that looks a lot like this, and it's basically just gives you the RVA and the address that it saw execution into. So mu is a two-stage unpacker, so we're going to miss that initially here. So we just allow this to continue executing for a little bit. We saw that it was executing inside of the mu address space, the RVA. We'll let that keep going a little bit more. And then once that's done, we should see, and if you can see the little dot moving around for the VNC, you probably can't, but it makes the mouse real jittery while it's running. Okay. This actually takes a fair amount of time to run, so there's a little bit of time dilation inside of here. So one of the things it found is that it found the fixed dump image to have RVA BB08, and the actual address that it found is going to be 40BB08, which is the actual original entry point here. Okay. So now what we can do is go over to the VM, and it's very important to kill the process inside of Windows before you start killing Ether. There's a pretty substantial bug that you'll have a lot of fun with if you don't do that. Something about rebooting the computer. Okay, so once we've done that, we can go inside the images directory, and inside of that images directory, we can see that there's a fix file. You get the original files that are going to have the OEP address inside of there, and then the actual binary is going to be inside of that. So now what we can do is we can load up IDA and start looking at the actual executable inside of here. Okay, so all we're going to do is pick the fixed address. Load that up and get this going. And so IDA's making noises like it's a little bit happier with this. It's actually identifying the valid functions. We get code data up inside of the graph bar. The functions actually have real code in them inside of garbage. Functions, there's actually a compelling list of functions that we can look at. The Flirt database found some stuff. And then inside of the strings, we actually get the good the things here. So in this case, NetBulls, I guess it was named because it had this string inside of it. So we get this out of here. Okay. Cross-references are all working, so this is generally just a good dump of the actual file here. And so we can explore around here and then begin the normal reversing process. So what this has done is it's effectively de-armored this thing. Okay. Okay. There are some problems with Ether. The biggest thing is that the unpacking process generates a lot of candidate dump files. In this case, it was only 2, but I've seen in some sort of in other packers that are a lot more difficult, there can actually be hundreds inside of there. So you want something that's actually going to generate some good stuff. So we need a better method to discover the original entry point. Import rebuilding is still an issue. So when we're looking through this, it'd be nice to have all the imports and that sort of thing. That's being added. I've got some beta code that's not really ready to be released yet, but it'll be there. But one of the nice things to do is that now we have a covert system. Let's do some analysis. Okay, so to modify our reverse engineering process, we're going to address it this way. So knowing what to look for is often the most difficult problem that new reversers have. And so figuring out what the flow of execution is inside of this will generate a lot better results from that going on. So IDA is focused on the function view, and what I'd like to do is extend it to the basic block view. And the reason I go to the basic block view is because a lot of unpackers don't necessarily have the traditional compiler-based function listing. But the software armoring and removal is made easy, and it works across a wide range of packers. Okay, so let's talk a little bit about Vera. So Vera is a visualization system to take advantage of this trace data. The goals that I had were I wanted to quickly visually subvert this software armoring process, and also find something that will enable access to various modules of the program. So any sort of parts of the initialization code, the main loops, and the end of unpacking code. End of unpacking, this is where the self-modifying code is going to be at, so we can pick out OEP easily and not get tripped up there. And this is all based on the dynamic runtime behavior. So if the code doesn't execute a certain path or portion of the executable, it won't be visible in here. And so we want to integrate it with existing tools. Okay, so what VIRA is it stands for Visualization of Executables for Reversing and Analysis. If you watch Firefly, it's the name of Jane's gun. I've been trying to find a program to name it a VIRA for a while, but finally got it. And it's a Windows MFC application that does OpenGL, and it's going to integrate with IDA Pro. It was a bug I was working on, but didn't get it out quickly. But it's a fast, small memory footprint program. So this is definitely a Fisher-Price, my first OpenGL MFC application. So when you go and look at the code tonight, try not to make too much fun of me, because, well, anyway, I've been writing bad code for many years. Okay. So.
Yeah, we haven't really gotten him beyond that yet. So in the VIRA graphs, what we're looking at really is each vertex or node in the graph is going to represent an address. That address that we're looking at is either an instruction address or it's the beginning of a basic block. All right? So there's two different views you can look at here. You can look at basic blocks, which is going to give you a little bit coarser granularity than the instruction view, because we collapse all of the instructions in a basic block into one node. The edges represent the transition or execution. As you go from one instruction to the next, you get an edge in the graph, and then during the execution, it's counting how many times that transition was made. The more times the transition is made, the thicker the edge is going to be in the graph. So basic blocks, for many of you that have had compilers, you're familiar with this, but all it is a fundamental grouping of instructions where there's no transfers of control except you just execute the next instruction, right? That reduces our graph size, reduces the data set size that you're looking at for the visualizations, and makes it at least possible to do commercial programs. Whereas if you're looking at the instruction view, that can be very good for trying to figure out exactly what's really happening and looking at it at precise instructions, but only for really small code. If you start looking at the assembly instructions, those of you who have done some reverse engineering know it gets pretty tedious, and that's true for the graph representations as well. Danny really likes the instruction view, though. It makes these nice, what he calls swoopy graphs, and you'll see those in just a minute, that you get these nice long arcs and streams of instructions.
It's good to present to management.
Yeah.
It's pretty pictures. So.
Unfortunately, if you try to do that with any real commercial software, the graphs are just too big to be usable. As we'll see with some of the small examples that we're going to do here, you get some pretty intense graphs if you tried to take something like Microsoft Windows and do it. So the edges, as we said, were just the transitions between addresses, and the thickness of the line is going to tell you how often it's executed. What it's not going to tell you, and what these graphs will never tell you, is if there's a chunk of code that's never executed in the path that you're running, you're not going to see it in the graph because it wasn't executed. So if you have code that only executes every 1,000 times that the program is run, you're not likely to see that, right? You're going to have to then, if you have some way of knowing it's there, good luck finding it and actually doing the reversing from the assembly code to find what's going on. But for normal executions, you're going to be able to see where there are loops because the edges will be thicker, and find concentrated execution. So you can tell loops where there are loops, but you can also tell which loops are executed a lot of times. So In the graphs, you'll also see that from some nodes, there are multiple paths going out. That's a decision point where you had to decide which path to take in your execution. And this is just sort of an overview of finding the original entry point. Trying to do that, you're using these basic block representations and edges. But to understand what's going on here, one of the things that happens is some color coding that helps you understand what's happening with the actual memory execution and where the code was in the packed or unpacked version. And Danny's going to talk about why he picked the colors he picked.
Okay, so identifying the portions of the executable that are interesting is what we're trying to do. So this is specific to the finding OEP problem. The first one, and each one of these colors is based off of two views. The first one that's going to look at is the dumped file that exists in the address or in memory, and then what it relates to inside of the packed file, because the memory addressing should be fairly similar. So yellow is anything that's normal, uncompressed, low entropy code. This will be anything inside of the section data. To generate the entropy, what I did is I took the algorithm out of Eero Carrera's PE file and used that to find this. So yellow will be normal stuff. Dark green, what this is it's going to be, it's going to represent something that's in a section that's not inside of the packed version. So normal code executes inside of these sections, which will come in here. Light purple is where the size of raw data on the disk image is going to be 0, which means it's allocating the space ahead of time, but it's not necessarily on the disk there. The two big things that I wanted to point at execution in was anything where the original packed executable had high entropy. So that'll be dark red. And if the instructions don't match inside of the packed executable, this would be light red. So dark red would be something that's like compressed or encrypted code. Light red would be something where you're doing, it's got the same low entropy, but it's not necessarily the same thing. So light red will typically show up for XOR decoding. And then lime green, this was put in to highlight when you have sections of code, like when you have a shifting decode debugger where it decrypts portions of its code, executes it, and then re-encrypts it, and then decrypts code back into there. Okay, so these were chosen really arbitrarily. Mostly I said, hey, I need a new color, and I did that. So I'm not red-green colorblind, but one of my friends is, and he looked at these graphs that I was building, and he said, that's great, but everything's brown. So what I did is I sat down with him, and I came up with another alternate set inside of here. It's inside of the uncommented code, or it's inside of the code. You can uncomment this and put it in, and actually you can change it to be whatever you want. So it's not necessarily a hard and fast thing. But if you have any feedback on this, I'd really appreciate it. Okay, so I'm gonna show it to you in a minute and quit talking about it in a second. But generally, the idea behind Vera is that you use Ether to generate an instruction trace. And then once you develop these instruction traces, it pass it off to an analyst system, which is going to have a program called GenGraph. And GenGraph uses the Open Graph Display Framework. So this handles all the arrangement of the vertices and edges and that sort of stuff. It's very similar to GraphViz, but unlike GraphViz, it can handle large amounts of data. So I've actually had up to a million vertices inside of here. And as long as you got enough memory, it's really good at this. So if you have need to do graphing, I highly recommend OGDF. From there, we hand it off to Vera, which is the OpenGL portion of this to actually do the rendering. Okay, so to get this to work, you run an instruction trace with Ether on your program. You transfer that trace file to your analysis box, run GenGraph, and then open the resulting GML file inside of Vera, and then correlate the data in that graph to your actual executable. So let's do a demo here. Okay, so we start by running Ether. We still have the ID that we're looking for here, and we use the instruction trace and give it the name of the executable that we're going to watch. In this case, it's mu netbowl. and then we're going to output that to a trace file. Once you have this, now you need to go over and actually start executing the program. So again, you need to have some way to actually stop the execution once it's gotten started. So we're just going to start it up here. It's going to start using all the CPU space or CPU time, and then we can start executing the program. So at this point, we'll do a time elapse here. We know that Muse or NetBull is running because we get this little icon in the lower right-hand corner. It's a pretty benign virus, so that's why I like to do it. So I'm going to stop execution of the program, go over here to Ether, and look at the trace file. The trace file is actually about 250 megs in size, but I've had it up to about 8 gigs, and it still handled that correctly. So over here on the Windows system, I've got just a Cygwin prompt, so I'm just going to copy that file over. Copy the trace file. And this is a good example. The reason I built these videos instead of doing a live demo is because there's nothing more boring than watching 250 megs of data transfer. So stop that there. Okay, so once we have that, now we can run gengraph. It takes the trace file that was generated by Ether. It takes the original executable so that we can do analysis on it, and then where it wants to be output. So in this case, it's going to be taken to the GML file, and it takes a little bit of time to grind through this. And inside of here, I build 2 different models of this. One is a basic block view, and one is the instruction level view, so you can swap back and forth. Okay, so now we start up Vera, and we're going to start by looking at the basic block view. And the interface for moving around inside of here is similar to the Google Maps view. You use your mouse to drag portions of the executable, and you use your mouse to basically just drag around and make it a little easier. Each one of these blocks is the actual address. So in this case, this green block right here will be a basic block that it found, and then the lines here represent execution. So the thicker the line, the bigger or the more times it's executed. So this is how you find loops inside of the program. Okay, so you can explore around. This is actually Muse unpacking system here. There's a secondary unpacker here, which correlates to what we saw when we were trying to unpack it. But things are kind of crowded, so it makes it a little bit difficult. But if we zoom in here, we can see that this address right here, 40BB8B, it's not the OEP address that Ether found, but it's pretty close to it. So, but here we see that it's this light purple, and light purple means that it's in section data that's not on disk, but is actually in memory. Okay, so now we can scroll out. We can see that it's executing inside of here. We'll zoom in, and we can see where the main blocks are being executed inside of this. You can find the places that are making the main decision programs because they'll have multiple branches coming out. Okay, so let's look at the instruction-based view. All right, exact same thing. We start out, the dark blue address right there is actually going to be the beginning of the address. These branches here, this will be the actual thing. The nice thing about the instruction view is that things are generally less crowded, and it really makes it a little bit easier to find out what the main branching one is. So in this case, it's this address here that's handling a lot of the decoding. So we're going to scroll down, and then once we zoom in, we can see that the beginning of the purple address is going to be this 40BB08. So in the case of this unpacker, it's moving all of its code inside of a section that has 0 size. But basically what you're looking for is any sort of long continuous block of instructions that the program executes. Okay, so that correlates back to our Ether dump. We get inside of here, we can look at the rest of the program. One thing to point out is that when we're looking at the execution of a program, these long lines right here, any sort of long continuous grouping of instructions is indicative of initialization code right here. Any sort of branch right here is a decision that's being made by the code. So we can use that to identify major portions. And then of course the the major loop. Okay, so zooming in here, we can find these addresses, and each one of these actually correlates to a portion of that. And then move out, and then what we can do now is we can go and look for instructions that are inside of here and correlate these back into IDA Pro. So if we take a look at this one here, 403 C80, and bring up a copy of IDA, we could just type that address in, and we'll see that it's the actual code right there. So this is the long portion of execution that's being accessed there. And we move back, we can actually see that this is the same value and so on. So this corresponds to the instructions that are there. Okay. Same thing with other addresses and that sort of thing. So that gets us the whole view of that. But the other thing that you really want to focus on is that a lot of these similar programs, especially similar algorithms, like let's say there's an LZH compressor or a base64, most people are going to use the common code that's out there. So you can actually identify portions of the executable that have that and use that for your identification purposes. Okay. So it's got a nice navigation interface here.
In particular, with a lot of the packers, you see very similar structure, and you're going to see the same kind of structures in all the different packers that Danny's going to show.
So this is a view of the netball virus that's not packed, so it doesn't have that decoder stub. So all of this is compiler-generated code, so the coloring is generally going to be yellow. But it has the same features as what we saw in the mu executed code. So in this case, we've got on the upper right-hand side, you can see the initialization point. There's a small loop right there, and then we get that same 3 level branch right there. And zooming in, we can get a look at the actual code inside of that. So now this next section is just going to go over what various packers look like when we've run it through this code right here, and allows us to get an idea of what the features are. So inside of UPX, we can see that UPX has this highly compressed handwritten assembly code that shows up as high entropy, and then purple, which is where the size of raw data is 0. But again, this program, the actual data right here, we get this initial loop, the initial 3-way branching, and everything runs. This is a zoom in on right after the unpacking code, and we can see that it has this BB08 address in purple. So this is flagged it as well. ASPAC starts out with the execution starting right here, goes into the unpacking portion, and then it transitions into this high entropy code. So the high entropy code is basically the data that it's decoded in place and gotten access to. Same thing with FSG, starts out with yellow code, which is a normal low entropy code, and then transitions into this. So this is a good time to explain or to show off how the graphs looked separately or look differently based on how OGDF has decided to render it. But in this case, it still has these same characteristics. We still have the long initialization, we still have the branching structure of it, and those sorts of things. Okay, mu, I like mu because it has lots of colors. We looked at this inside of the demo, same sort of thing. In TLOC, which is a pretty hardcore packer, this starts out and goes through a whole bunch of different changes. So TLOC actually reuses a lot of instructions as it's executing and does this dynamic stuff. But over on the right-hand side where you've got this red portion, this is actually going to be the netball virus. And we can see that it still has that same structure with the initialization and the actual code inside of there. Okay, so this is all good for my canned netball virus, but what I wanted to do was look at something that's modern like the MEBRU. So what I did is I took the latest sample that we had on offensive computing and ran it inside of this. And one thing about, just show of hands here, has anybody reversed MEBRU? Okay, that's kind of a pain. But it seemed to be just idling, and it seemed to be in some busy loop for a long period of time. And so I ran it through this, and I was sort of wondering was it actually executing or not until the next morning when my friend, the network manager, called me up and said, hey, your box has a virus on it. And I was like, oh, gee, thanks. I knew that, though. So what MEBRU is it's a hybrid user mode and kernel-based malware system. So what we're going to try and do is figure out where it's actually dropping that kernel virus. So when I ran it, the initial analysis showed that it was dropping a driver, and basically what it was doing is it was sitting inside this busy loop. I guess it's just waiting for you to get bored inside of here. I don't know why it would be calculating things for 30 minutes. Maybe it's figuring out a Mersenne prime or something. But after that, it would move on to the rest of the program. So when I'm executing things inside of Ether and Vera, I start it up, let it sit for about 5 minutes, and then move on. And then once it got to that, it transitioned out of this section. So after I let it sit for more than 30 minutes, it would go out here. And then it would move inside of this main unpacking loop, which is inside of the program. So it really exposed a lot of the structure of the virus for what it was trying to do. So this is the entire view of the program. It starts out here. There's a blue address right here, which is always a starting point. It goes to this 30-minute initialization point. Once it's done there, it finishes with execution or initialization, and then we can see that it actually has 3 main components to it. The first one is the main decoding portion, where it's taking the loop and writing that out, and then we can see that it has these other 3 ones here, and I didn't take the time to actually look at that. But when it's done executing, we can see that there's an actual kernel code insertion right here, and we can use that to actually grab the file. Okay.
So Danny's been teaching courses in reverse engineering for a while now, and one of his recent classes, he took the Vera tool, and after they had completed the week-long course on reverse engineering, did a quick user study to see what kind of responses real users had. As you might imagine, doing a significant user study with this kind of project is rather difficult because there aren't that many reverse engineers out there that have a lot of experience. So the group that he did this with is a fairly small group, but it went all the way from 2 people who have never done reverse engineering before, and this was their first experience, to some people that do this quite frequently and are quite experienced with it. So he analyzed 2 different samples of NetBull, had them analyze rather 2 samples of NetBull with UPX and mu packing so that they get 2 different versions and look to see what kind of results they get. So they're looking at the same series of tasks that Danny has talked about doing on finding OEP and things like that. So we asked them about the efficacy of the visualization tool for each of the examples, and here were the tasks they were specifically supposed to perform. The first one, of course, is to find the OEP, find that entry point and be able to identify it or not. Then look for, after the execution, the packer code, the initialization, the main loops in the executable. So the first question is, did they or did they not find the original entry point? The 2 users that you see had a problem here with at least one version of the packed virus were the 2 new users who had never done reverse engineering before. Everyone else found the original entry points, and one of the new users actually found one of the entry points. For initialization, in one case, all of them get it. And in the other, with the other packer, we again have the new users not able to find the initialization. Main loops they were more successful with. We just had 1 failure in this case. But as you can see, even people with very limited experience are having some success, at least using this tool. The overall evaluation, though, we asked them in lavender, are you likely to use this again? Would you want to use this tool again? And everyone said yes. And they also said that yes, they would recommend it to others who wanted to do reverse engineering as well. So that gives us some feeling that there's, you needed a better way to do some of this, and the user study provides us with some feedback that it is useful. But some recommendations came out for improvement, and since Danny has to implement them, we'll let him talk about what those recommendations are.
Okay, well, the biggest one was that there needs to be a way to identify the beginning and ends of loops, which is valid. That wasn't in the original one, but it's easy enough to add. A lot of times, many of the loops became overlapped and became convoluted. So this is something that was actually fixed by switching to the instruction-based view. And another comment was, it'd be nice to be able to enter a memory address and then see which basic blocks actually match that. So there's a couple of ideas for future work. There's going to be just general GUI and bug fixes. Stabilization of Ether is big on the list too, because it rebooting is not cool. So memory access visualization is the next thing that I'll look at. System call integration, and especially function boundaries. So once it gets past that unpacking code, getting those system calls in would be useful. And then providing some sort of interactivity with the unpacking process, so being able to stop it once we get to a candidate OEP. And since Ether has this nice system to single-step processes and analyze memory and that sort of stuff, it'd be nice if it used with stuff like WinBag and OllyDebug and IDDebugger. Okay, so conclusions. The visualizations make it pretty easy to find OEP. You don't actually have to do any statistical analysis outside of the entropy. The program phases are pretty easy to identify. The graphs are simple. I showed this to some mathematicians I work with, and I was prepping them for complicated graphs because they're pretty complicated to me. And they looked at me and looked at the graphs and giggled, and they said, "That's not there." So they told me to put in a bullet about them being simple. And the preliminary user study says that it holds some promise for speeding things up. Okay, so for those of you that are going to try and recreate this at home, to get Ether installed, I just wanted to go over some bits that'll save you a lot of time. The first one is install a 64-bit version of Debian Sarge. That's the only distribution it works on, and I believe they've gotten past their SSH problems. And then install Ether using the instructions on their page at Georgia Tech. It's actually very thorough. And when you're setting up an analysis image, this is just going to be a 32-bit version of Windows with Service Pack 2, not 3. And you need to disable the following things: dep, large pages, and multiple CPUs. But that's all inside of the Ether instruction. The other thing is be sure to kill the target inside of the Windows system before stopping Ether, otherwise you get a reboot. Okay, so some closing thoughts. Ether's really awesome. Artem and Paul did an excellent job with this. And if you get one thing out of here, I'd really like you to take a look at it and see if you can incorporate it there, because it hasn't gotten a lot of traction when they released it. The source, the tools, and the latest slides can all be found at offensivecomputing.net. As soon as I get back to my hotel room, I'll post the tools and slides for you to look at. And if you do use this tool, I am trying to socially engineer a PhD out of my advisor. So if you could give me some feedback, that would be good. Also, a more thorough treatment of this is going to be at VisSec 2009 in an academic format. And so all these people were awesome. So thank you very much. Thank you. All right, so we got some time for questions. Yeah. Static executables? Yeah, I mean, how you generate the data. In this case, I'm just looking at so the question was, would it be possible to modify Ether to look at static data? And the answer is yes, but I took the dynamic runtime as my main tool here. It'd just be a matter of building the graphs up and putting it in that GML format.
Over here.
Yes, Eric.
So you mentioned your graphic library does different views sometimes based on loops. Is there a way to get that static so you can see the same thing every time you recognize it?
So the question was that it generates things that are slightly different each time. Like you notice that the starting point was in the lower left-hand side and upper right-hand side. No, I didn't know how to do that. I'm sure it's possible, and I could probably do some graph inversion to get that going, but that'd be a great place to start. So it's slightly non-deterministic when it does that. So.
Yeah, I think you can actually tell it to locate specific nodes. So, for example, the blue node that is the first place that's executed could always be located in the lower left corner, but Danny hasn't worked with that as much as some other students have, and did great taking it from 0 to 60. So,
I'll do better.
yeah, that social engineering goes both ways.
Anybody else? Yes.
So having people work with UPX and actually find the OEP is kind of not that interesting because UPX will look like itself.
Right. So the comment is that getting things to work with UPX is not that interesting, and you can get people to unpack that themselves. That's correct, and I would agree with that. This is just to show that the reason UPX is in there to give a wide overview of lots of packers and show that it works on each one of those. So, yeah, okay.
Secondly, having people who aren't familiar with reverse engineering work with this tool that's the only tool they know about that helps unpack it isn't necessarily interesting to have them all to recommend that.
Okay, so the comment was that having people that are haven't really done reversing yet and have not used any other tools to do this isn't necessarily a good thing. But there was only 2 people in there that had a low amount of skill with doing this, and the previous week had been spent dealing with the manual way of unpacking. So they had a pretty good view of how to unpack across a wide variety of packers already. And so this is just a neat trick that I showed them. So did I address that? Okay. All right. Anybody else? Okay. Thank you.